Okay, cool. So it's my pleasure to introduce Daniel Grier from the University of Waterloo, who's going to be talking about quantum advantage from interactive shallow Clifford circuits, which has been a really, really interesting topic of the last few. There's been a progression of work over the last few years, leading up to the work that Daniel's going to be talking about today, and it's been a really, really interesting line of research, which I think, I think it's going to be a really interesting seminar. Okay, thanks, Daniel. Take it away.
All right, thanks for that introduction. Yeah, so I'm going to be talking about some quantum advantage result from low depth quantum circuits. This is joint work with Luke Schaefer. We're both postdocs at the University of Waterloo, but this work was actually done while we were both students at MIT. And I just want to stress sort of what we already talked about earlier. This result that I'm going to talk about today is even sort of difficult to state what the result actually is. And so if there are any questions that come up while I'm talking about it, just feel free to interrupt me and ask them. I sort of baked that into the time for the talk. All right, so without further ado, let's just get started. So the goal of this talk is going to be one that I think we can all pretty easily get behind, is to devise some task which is solvable by a quantum circuit that can't be solved by a classical device. So there's some things that we need to sort of break down about what we actually mean here. So first, what do I even mean by a task? So in the sort of traditional line of quantum supremacy results, I don't mean that something that is necessarily needs to be useful or has any sort of immediate application or anything like that. And you might say, well, there's already a whole host of sampling-based problems that satisfy this goal. And yet these are very impressive, and we're already starting to see some of the fruits of that labor experimentally. And yet, as these protocols get closer to physical realizability, you need more and more assumptions which are sort of non-standard to complexity theory, which is a bit unfortunate. And so, what if we tried to sort of mitigate that problem as much as possible? So I'm going to sort of add a restriction to my goal here, which is I want to prove such a separation with sort of as few computational assumptions as possible. And as soon as you add this restriction, it's sort of not clear anymore what task you would even reach for, because this is, I've asked for quite a lot here. So instead, I'm going to change the goal slightly. And instead of comparing the full power of quantum computation to the full power of efficient classical computation, this question of BQP versus P, let's instead compare the power of constant depth quantum computation to sort of similarly restricted classical computation. And this question of similarly restricted is really the whole name of the game. So can we show that there's like a constant depth quantum circuit that can't be simulated by a constant depth classical circuit, or even a log depth classical circuit, and sort of how far can we push this separation is really the question. So this whole line of work was started in 2017 by Bravyl-Gosset-König with this sort of breakthrough result, which showed that there is a task which is solved by a constant depth quantum circuit that can't be solved by any constant depth classical circuit with bounded Fanon gates. So by bounded Fanon, I mean every gate acts on at most constantly many bits or qubits, and constant depth, of course, is just there's constantly many layers to the circuit. So in the parlance of complexity theory, this is sort of a separation between the classical class NC0 and the quantum class QNZ0. And it's worth emphasizing here that this is just a separation full stop. No conjectures or assumptions are necessary to prove this result. So there's just this task in QNZ0 that you can do that can't be done with an NC0 circuit, which is fairly remarkable. And in fact, there's some additional nice properties about this problem. It has a very simple gate set. The gate set is just classically controlled Clifford gates. And in fact, these classically controlled Clifford gates are local on a 2D grid. So there's also a nice simple circuit topology as well. And because this problem is going to sort of pervade sort of the rest of this talk, let's just spend a few moments trying to understand this problem. So this problem was called the hidden linear function problem by Bravyl-Gosset-König, but you know, that has to do with some sort of algebraic structure of the problem. And I'm not going to present it in that way. So that's the last I'll refer to it as that. Instead, I just want to sort of think of it as this very simple relation task about quantum circuits. So imagine you have some quantum circuit Q for every n, and then your task is you're given some bit string x, and your task is to output some bit string y, which has non-zero amplitude in the state after you've applied Q to x. Right, so this is, in some sense, a strictly easier problem than the analogous sampling problem. So we usually think of the sampling problem as drawing from this distribution, where now the task is simply to pick any element from this distribution you want and report that. And clearly, if you could do the sampling problem, then you could also answer this relation problem by just first doing the sampling and then outputting whatever you have. On the other hand, this task is harder than a lot of problems that we sort of traditionally think of in complexity theory, which are decision problems, where the output is only a single bit. Now notice y here is many bits long. It's as long as the input. And it's not too hard to see that if y were only a single bit, then it would only depend on constantly many input bits of x as well. And in that, this is just based on some sort of light cone argument. And because of that, you know, if y were only a single bit, then there actually would be a constant depth NC0 circuit to solve this problem. So it's actually pretty integral that we have this large output, so we can get all of the correlations between all the bits. So that's the Bravyl-Gosset-König task. And you might say, well, this is like a very fair comparison, right? We're comparing quantum depth classical circuits to classical constant depth bounded fan-in circuits. Like it's exactly like sort of like a one-to-one comparison. But on the other hand, sort of unfortunate thing about these circuits is that NC0 circuits are extremely weak, right? It's like these bounded fan-in constant depth circuits, like they can't even tell if all of the input bits to the circuit are 1. Like it just can't even compute that function. So it would be nice if we could sort of keep all of the nice properties of the QNC0 circuit that we have, and yet show that sort of larger and larger classes of classical circuits or classical devices can't simulate such a problem. And there has been some work to that regard. So there is this follow-up work by Bene Watts, Schaeffer, and Tal in 2019, where they improved the BGK result to have unbounded fan-in circuits. So an unbounded gate is one that can act on as many input bits as it wants. So you can, for instance, you can compute the AND of all the input bits or the OR of all the input bits if you like. And then in the complexity theory parlance, this is, these circuits are called AC0 circuits. And so what this result did was it took the exact same problem and showed that in even larger classes, these AC0 circuits can't solve these problems. So, you know, there's a very natural progression here. It's like, okay, how far can we actually push this? And it turns out that we think that there's either something is going to have to give here. Either we're going to need sort of a new ingredient, or we're going to see like a very novel proof technique idea. And maybe that exists, but okay, we didn't know how to do this. So we added this new ingredient. And this new ingredient you may have seen from the title is interactivity. And so what we're going to do is we're going to take the Bravyi-Gosset-König task, and we're going to introduce interactivity into that task. And so this theorem is sort of difficult to state, and so I'm going to sort of slowly reveal it to you sort of here in its sort of informal statement, and then I'll get more and more formal and more specific about what this task actually is later. But at a high level, the theorem statement is as follows. So there's a 2-round interactive task, which can be solved by a constant depth quantum circuit with bounded fan-in gates, such that, and now the result comes in 2 flavors. So there's an unconditional result, which says that this interactive task cannot be solved by a constant depth circuit with unbounded and or not in parity gates. So now we have sort of an unconditional separation with AC02, this complexity class. And then there's a sort of a conditional complexity theoretic result as well that says, you know, assuming that the complexity class L is not equal to the complexity class parity L, then this interactive task also can't even be solved by logarithmic space Turing machines. So I just want to take a moment to sort of put all of these results that I just talked about on the last few slides into context. So we started out with NC0 circuits, so bounded, fanded, and or not gates. And Bravyl-Gosset-König showed in 2017 that there's some relation problem in QNC0 that can't be solved with these NC0 circuits. And then contained in the class NC0 is the class AC0, which consists of unbounded fanded and or not gates. And this was the result of Bene Watts, Schaefer, and Tal in 2018 that showed that the same relation problem also can't be solved by AC0 circuits. And then in this work, we show that there's an interactive task in QNC0 that can't be solved in the class AC0 too. So this class strictly contains the class of unbounded fanded and or not gates because it has a parity gate, and AC0 circuits cannot compute parity. So in some sense, it's sort of a strict improvement on the previous results, albeit we needed to add this sort of ingredient of interactivity. And then contained in AC02 is the class of NC1. So everything I've talked about so far has been constant depth. Now NC1 is NC circuits, but now they're allowed to have log depth. And then contained in NC1 is this class L, which consists of log space Turing machines. And then contained in the class L is, containing the class L is the class parity L, which one way you can think of it is the class which can evaluate polydepth C0 circuits. And so something to notice here is that the first three inclusions here were strict. We actually can prove that each class contains the next. So we know that we're making some progress here. But for these last two inclusions, we don't know. Though like it's usually assumed in the complexity literature that these classes are separate. But supposing that we did have such a separation here, that one of these inclusions were strict, then we would get an even stronger result about this interactive task. So for example, if it were the case that one could prove that the class NC1 is strictly weaker than the class parity L, then it would be the case that there's some task, interactive task, which can be solved by a constant depth quantum circuit, which provably can't be solved by even a log depth classical circuit, which is fairly remarkable. I guess it's also worth pointing out here that this class parity L is not super powerful. It's contained in the class NC2, which of course is contained in the class P. Okay, so that's sort of the landscape that we're dealing with, these very small complexity classes. So I've sort of put it off sort of as long as possible now. What is this actual interactive task that we're dealing with here? So just like I defined the Bravyl-Gosset-König task and sort of in terms of what the quantum machine was doing, and then the goal was to sort of simulate what the quantum machine was doing, I'm going to do the exact same thing here. So I'm going to describe an interactive task where there's some sort of challenger asking questions to some quantum device. And then the goal for the classical device will just be to sort of simulate any transcript that the quantum device could have produced. So we think of originally, before the protocol even starts, the quantum circuit has in its possession what's called a cluster state. So if you haven't seen this before, it's just you think of a grid graph where you put a plus state on every vertex of the grid, and then you apply the C sign gate on every edge. So this is just sort of some large entangled resource state. And it's actually not too hard to convince yourself that this entangled resource state can be constructed in constant depth by a quantum circuit. So this is what the quantum circuit starts with. And in round one, the challenger is going to specify some bases, either X, Y, or Z, for all but a few of these qubits in this grid. And the quantum prover will just take those bases, it will measure the corresponding qubits in those bases, and it will return the measurement outcome. So it just measures those bases, it just measures those qubits and returns the measurement outcomes. And then in the second round, the challenger will specify bases for the remaining qubits, so the qubits that weren't already measured in the first round. And the quantum prover will do exactly the same thing. It'll measure those qubits and report the measurement outcomes to the challenger. So as a little example here, I've written a 2x3 grid. So sort of before the protocol starts, you can think there's some quantum device that has in its memory this cluster state. It's prepared this cluster state. And then in round one, the prover, or the challenger rather, is going to specify bases for most of the qubits. Let's say these for the first 4 qubits here. So the quantum device will rotate those qubits accordingly and measure. and report those measurement outcomes back to the challenger. And then in round 2, the challenger will specify bases for the remaining 2 qubits. The quantum prover will rotate accordingly and return those measurement outcomes. And that's all it's doing. And once again, a classical simulation of such a task is just like your goal is to return any valid transcript that the quantum machine could have produced. So, you know, what really is the difference between a quantum simulation and a classical simulation here? We're actually going to get a lot of mileage out of this. So imagine I have some quantum circuit faithfully executing this protocol that I just mentioned here. So after round 1, it measures these bases, and what it's got left over, what its sort of internal state is just some quantum state that's left over from measuring what we had before, right? And then in round 2, it's asked to measure that state again to report some measurement outcomes. But notice what happened here. Like we had the state between round 1 and 2, but then we sort of destroyed it by measuring it again in round 2. So we can't really have gone back to the state that we had between round 1 and 2 because we've destroyed our state. And there's this sort of like no cloning theorem, which is like sort of getting in our way. So all we can do is like sort of go all the way back to the beginning and start the protocol over again. But then if I'm faithfully executing the task, there's no reason to expect that I'm going to get the same measurement outcomes that I got in the first round again in this, like, or in the first sort of phase that I would get in the second phase where I repeated this whole protocol over again. So there's no guarantee that I'd ever get back to the same state again. Now contrast this with a classical device. So if I had a classical simulation of what this protocol was doing, then after the first round, right, we asked the classical device to report some measurement outcomes consistent with what the quantum device would do. But now the classical device actually has like a classical description of what the state should be between rounds 1 and 2. Right, so this is really like sort of the key idea of this work in some sense, is that, you know, any classical simulation that you have must have a classical representation of the state between those rounds 1 and 2. So what this allows you to do is after you make some round 2 measurement, say you ask it a particular set of bases to measure and it makes those measurements, after you've asked it to do that, you can then rewind the classical device back to its state right after round 1 and ask it a different set of questions than the ones that you originally asked. So you can ask many, many times. So you can sort of, in some sense, this is like having the ability to sort of make a non-collapsing measurement on a state, because you make a measurement on the state and then you rewind it back to the state of the machine where it had that exact same state. You can just keep making measurements. And because we're assuming that the classical device is actually passing this task, it gives you useful information about those measurement results. Okay. So that's, you know, we're going to get a lot of mileage. That's the interactive task. So I'm going to state the theorem again in slightly more formal terms, now knowing sort of what exactly this interactive task is. So suppose that we had some classical simulator R, which solves this 2-round measurement problem I just mentioned on grids of width m. Then if m equals n, so now so imagine that the cluster state that we started with was an n by n grid. It's a square grid. Then what you can do is you can leverage the answers from the classical simulator to solve a parity L-hard problem. So if you were to sort of write this out in sort of complexity speak, this would be like the class parity L is contained in the class AC0 that has access to an oracle for this classical simulator. If m equals 2, so now we're dealing with a very long but narrow grid. Then you can leverage this classical simulator to solve problems in NC1. And if m is very thin, if it's just a line, then you can leverage this classical simulator to solve problems in AC0 6. So the 6 just means like AC0, but with the addition of mod 6 gates. So this is almost exactly the full statement of the theorem. In fact, I've lied to you a little bit. These reductions even require randomness, which I haven't specified here, but for right now, that's not important. This is like the main idea. Now, I've sort of already warned you about this, but I'm going to warn you again because it comes up a lot. This theorem does not say that we can have a QNC0 circuit, a constant depth quantum circuit solving a parity L-hard problem. What it says instead is that if you had a classical simulator for this QNC0 task, then you could leverage that classical simulator to solve a parity L-hard problem. But the quantum machine itself cannot solve the parity L-hard problem. Okay, so now that we have the theorem, it's really easy to get a lot of the consequences that I talked about sort of in the first part of this talk. So I just sort of picked one out here as random. So imagine that, the corollary is that there's no AC02 circuit that solves this 2-round measurement problem. So imagine by contradiction that we did have such an AC02 circuit. Then if we look at this sort of m equals 2 case here, we see that we can say that NC1 is contained in AC0 with oracle access to AC02, right? Because I've just sort of instantiated my oracle R by AC02. But AC0 with oracle access to AC02 is just AC02 itself, right? The AC0 is not adding anything there. So now we have that NC1 is contained in the class AC02, which we know is false. So this is just false because of a famous theorem called the Razvarov-Smolenski theorem. So this just can't be true. So our supposition was false. So there's no AC02 circuit which solves this 2-round measurement problem. Okay, so and for the remainder of this talk, I'm going to try to convince you of the m equals 2 case. I'm going to try to show you that if I had a classical simulator for this 2-round measurement problem, I can use it to solve an NC1 hard problem. But before we do that, I thought it might be a good idea to sort of break for questions that you might have about the model or the theorem before we get into the sort of details of the proof. So maybe I'll just wait a few seconds here to see if anybody speaks up.
Daniel, can you explain more about the parameter m, the width? I lose on track of this parameter.
Yeah, so the width, so that's a good question. So the parameter m is talking about sort of, it's in reference to this cluster state that we started with in like that the quantum computer starts with before the protocol even starts, really. Like if the grid that you start with is sort of like a large square grid, that's sort of like the hardest case. Like those measurements in some sense are the hardest measurements to make. So that's, if you can simulate measurements on a large square grid, then you can show that you can leverage those measurements to solve a parity L-hard problem. But on the other hand, if you have like a thin grid, like if the grid that you start off with is like a 2x(n) grid, so it's like very long, but it's thin. These measurements are slightly easier to make, but you can actually still show that if you had a classical simulator for measuring such a grid state, then you could use it to solve NC1.
Okay, so it generates m by n, and in this case, m equals 1 means like it's like 1 by n. That is.
Exactly. Yeah. Exactly. Okay. Well, if there are no other questions, I'll move on. But if it just like took you a while to get up the courage to ask your question, then just interrupt me, and that's totally fine. Okay. So how do we go about proving such a thing? So the main technique is going to be a simple reduction. So we're going to show that if you have some classical device which solves this 2-round measurement problem, you can use that classical device to solve what I'm calling the Clifford gate multiplication problem. And the Clifford gate multiplication problem is very aptly named. It's just you're given a list of 2 qubit Clifford gates, G1 up to Gn, and you're just asked to multiply them together and compute what their product is. And it's a theorem that this Clifford gate multiplication problem is NC1 hard to compute. And we'll see why in a little bit. But not only that, not only is it hard to compute, it's actually hard to compute even when the product is promised to always be either the identity or Hadamard tensor Hadamard. So we're going to use that in a bit. So at a high level, how is this proof outline going to go? So we have these sort of 2 rounds that we get to play with, and each round is going to sort of serve its own role. So in round 1, what we're going to do is we're going to use this idea called measurement-based computation to force the classical device to create the state where we've applied G1 up to Gn to the 0, 0 state. So in some sense, by making the measurements, you're affecting this transformation G1 up to Gn on the 0, 0 state. Then what we're going to do in round 2 is we're going to use our ability to measure the state multiple times. Because of this fact that we have rewinding, we're going to use the fact that we can measure the state multiple times to determine whether or not the state is 0, 0 or plus plus, right? If the state were 0, 0, then we know that the product G1 up to Gn must have been the identity. And if the state is plus plus, we know that the product G1 up to Gn must have been Hadamard, tensor Hadamard. So if we can figure out what the state is, then we can figure out what the product of the Clifford is, which means we can solve this NC1 hard problem. So that's the whole idea. Now, before I actually go into the details of those 2 rounds, this is sort of like a caricature of what's actually going to happen. But before I go into those details, I thought it might be good to give sort of like a very brief review about the Clifford group and the poly group, because they're going to be sort of integral players throughout the rest of this proof. So many of you have probably encountered the Clifford group before. It's a very important subgroup of the quantum operations. It's generated by the C0 gate, the Hadamard gate, and the phase gate. And okay, so it's generated by these gates, and it's known that it's thought that these gates aren't universal, and yet they sort of show up everywhere. They're very, very important. They have a lot of nice properties. So one of the nice properties that they have is that they can be defined as the normalizer of one of their subgroups, which is the poly group. So what does it mean to be a normalizer? So we say that the Clifford group normalizes the poly group if, for every Clifford that you have, if you take a poly element and you conjugate it by that Clifford, you get another poly element out. So Cliffords map poly elements to poly elements under conjugation. And in fact, not only do Clifford elements do this, you can actually define the Clifford group as the set or the group of operations which normalizes the poly group. And this fact is actually going to allow us to do a lot of cool things. And one thing we can do is we can use it to represent states, not by the traditional sort of state vector way, but by the group of poly elements that stabilize them. So I say a poly element stabilizes a state if when you apply the poly element to that state, the state remains unchanged. So the state is an eigenvector of the operation. So for example, if we take the 0, 0 state here, its stabilizers are the I tensor I poly, the Z tensor I poly, the I tensor Z poly, and the Z tensor Z poly. Now I've like omitted the tensors between these polys here. That's sort of like a standard sort of notational thing, but that's what it means. So now we have the stabilizer group. What happens when we apply some circuit C to the stabilizer group, to the state? So it's not too hard to check. It's sort of an exercise that whatever stabilizer group I had before, so in this case I had II, ZI, IZ, and ZZ, whatever I had before, the new stabilizer group is whatever I had before, except it's conjugated by the Clifford circuit. It's not too hard to convince yourself that this is in fact the case. Like these new polys or these new operations will stabilize your new state. And because the Clifford group normalizes the poly group, all of these elements are themselves poly. So we're just sort of keeping track of poly. So we're just always sort of keeping track of a group of poly elements. Okay, and this will sort of feature prominently later on in the talk. So let's go back to this fact now about Clifford gate multiplication. I said that it was NC1 hard. How might you go about proving something like this? So you can look at the Clifford group on 2 qubits, and you can mod out by the poly group on 2 elements. And we saw before, right, this is once again coming to the fact that the poly group is normal in the Clifford group. So this quotient group is a legitimate quotient group. And not only is it legitimate, it's actually isomorphic to S6. So what that means is that now we can sort of view the multiplication of 2 qubit Clifford gates, mod polys, as the composition of permutations on 6 elements. And why is that it's important? Well, that's important because we know from the theory of branching programs, and in particular Barrington's theorem, that computing the composition of elements in S6 is NC1 hard. All right, so if computing the composition of elements in S6 is NC1 hard, and we can embed permutations into the Clifford group on two elements, then it must be the case that this Clifford gate multiplication problem is also NC1 hard. Okay, so that's all I'm going to say about the Clifford group for now. So this is the exact same slide that you guys just saw, but you just a sort of a roadmap to remind you what this proof outline is going to go like. So in round one, we're going to use measurement-based computation to try to create some state where we apply G1 up to Gn to the 0, 0 state. And then our goal will be to deduce what G1 up to Gn actually is. And the way we're going to do that in round two is by making a lot of measurements on the state to determine what it actually is. Okay, so what are the details of these two rounds now? That's really the important thing. So if you haven't seen measurement-based computation before, it's simply this idea that suppose you have some sort of large unitary that you want to apply. Instead of doing sort of the normal thing where you have like gates and you're like concatenating them together, composing them together to sort of synthesize the unitary, what you can do instead is you can start with sort of a large resource state and make single qubit measurements on that state. And then after you've made sufficiently many of these single qubit measurements, you'll have affected that transformation on the remaining qubits of the resource state. So I've drawn sort of an ideal situation of what that might look like in our case. Remember, we're sort of narrowing in on this case where we have like a long but narrow grid. So sort of the ideal situation for us would be, well, we ask the classical device to make these measurements on this state. And what we would have left over on the remaining two qubits is exactly G1 up to Gn applied to the 0, 0 states. This is like, sort of a promise of MBBC. But how are we actually going to, what is the sort of technical lemma that we're going to use here to get this to work out? So we're going to use a lemma by Rausendorf, Brown, and Bravyl. They sort of pioneered this one-way computation technique, which says that if you want to apply some 2-qubit Clifford gate G, it suffices to measure some 2x20 grid in some particular x and y bases, and such that after you've measured at like 18 of these qubits, like the number 20 doesn't really matter, it just has to be sort of a sufficiently large constant. But after you've measured a sufficient number of these qubits, what you get on the unmeasured qubits is exactly the gate that you wanted to apply. So you have G applied to 0, 0, except now it's corrupted by this poly error term, where the poly itself depends on what measurement outcomes you got from the x and y measurements. So sort of pictorially, so imagine we had this sort of 2x20 grid here. There's some set of measurements on the first 18 qubits that you can make that correspond to the application of G. And after you've done that, you have the state where you've applied G, but you've sort of accidentally applied this poly term as well. And what you can do is you can take this fact and just sort of apply it iteratively over and over again to this chain. So you can do it, and then you can apply the second gate, and so on up until you've applied G1 all the way up to Gn. Right, but of course, like, if you look at these two states, the one that we wanted and the one that we got, and you squint, you realize like these two states, they're not the same, right? The state on the bottom, the one that we are actually getting, is corrupted by these sort of like interleading polys, and these polys are actually going to cause sort of a lot of headache for the proof, and so we're going to need to eliminate them somehow. So why are these polys even coming up in the first place, you might ask? Like, usually it's sort of the guarantee that you have for measurement-based computation is that you just apply the transformation that you want to apply. And the reason that we get that is because the usual measurement-based computation techniques are adaptive. So how might those arguments go? So you go to apply your first gate, and so you try to apply a first gate by making a particular set of measurements. And so you've applied your first gate, but you've also created this new poly error. But instead of just applying the second gate G2, just sort of in a black box way, you see what poly error you got in the first round, and then you apply the gate, which sort of rotates away that poly error before you apply your next gate. So you apply sort of G2 times P1, and then that P1 is going to cancel with the P1 we got from the first gate, and then so on and so forth. You just sort of iteratively, adaptively cancel out the error that you got in the previous round. But unfortunately for us, we don't really have that kind of time, right? So if we wanted to simulate this sort of adaptivity in our proof, it would require many rounds of interaction, and we only have 2 rounds of interaction. So there's like, we definitely can't do something like this. So we have to find a new way around this problem. And so, one of the first things you might think to check is like, well, maybe we can just, use some sort of Clifford magic to save us, right? So there's this fact that if you have any Clifford gate G and any poly P, you can sort of take the poly on one side of the gate and push it to the other side of the gate via some conjugation rules, and it'll still be a poly on the other side. And once again, this comes up from the fact that the Clifford group normalizes the poly group. So sort of the upshot of this is that instead of having the sort of like gross interleaving polys intermixed with our Clifford gates, we can sort of push them all to one side, and now we only have one poly that we need to correct for. And you might think this is like, well, this is great, right? We just have this one sort of poly error correction term. Let's just like rotate the state such that it's no longer in that poly error term, and then we're good to go. Well, the problem with that approach is sort of subtle, which is that if I want to compute this poly P here that I just mentioned from the individual error terms, from the individual PI error terms, then this task itself is an NC1 hard problem. So sort of recall what we're trying to do. Like the goal of this proof is to use the results of the classical simulator and use them to solve an NC1 hard problem. But if in the course of our reduction, we have used the power of NC1 itself, then we sort of haven't shown anything interesting here. So in some sense, like we actually can't know what this poly P is that's hanging out in front of our G1 up to Gn. Because if we could just know it exactly from right now, then we would have been cheating. But now this should really scare you, right? It's like, so if you think about this like in terms of quantum channels, like imagine that you just had the quantum channel that like took some state rho and applied a random poly P to it, one that we didn't know about. Then this is actually just the completely depolarizing channel. It just sort of obliterates all of the information about your state. And so you might think like you're just like totally stuck. You just like, because you haven't like done this technique adaptively, like there's just no hope, right? But the thing that we haven't used yet is the fact that we've got another round to play with, and we've got this rewinding capabilities. So the idea is that, a single measurement may not reveal sufficient information to determine the state. In fact, it sort of provably doesn't reveal sufficient information to determine the state. But if we make sort of many sort of non-collapsing measurements through this rewinding technique to the state, we actually can figure out something about the state. It will suffice. So how is this going to go? This is itself kind of tricky. So the plan here is we're going to use repeated measurements of the state, and we're going to sort of slowly deduce what the stabilizer group of the state is. So this is where the stabilizer group comes in again. So just to remind you, we're trying to distinguish between these states 0, 0 and plus plus, and I've sort of written their stabilizer groups out here, right? So the plus plus stabilizer group is different from the 0, 0 because all of the sort of z terms are changed to x, so they have like a completely disjoint stabilizer group. But there's an important thing here that I haven't mentioned yet, which is the fact that we don't just get the 0, 0 or plus plus as I mentioned before, right? There's this corrupting p that's hanging around. But the really nice thing about having a corrupting poly hanging around is the fact that it actually doesn't really change the stabilizer group all that much. All it does is sort of affect the sign group of the stabilizer group of the stabilizer group. So if we can sort of figure out what the stabilizer group is modulo signs, then we're sort of back in business, because then we can just, if we see that the IZ or ZI is in there, then we can deduce that the original state was 0, 0 and solve our problem. So that's exactly our plan. We're going to try to figure out what the stabilizer group is, sort of modulo signs. So we're going to do that by making poly measurements on the state in round 2. So I just want to talk about some like relevant properties of poly measurements on states. So at least like what we need from them. So if I measure a poly P on a Clifford state's psi, what it means is if that poly P happens to be in the stabilizer group of psi, then the outcome that you get from the measurement is going to be whatever sign that poly appeared as. So if plus P was in the stabilizer group, then when you measure, you're always going to receive the outcome +1. And if minus P were in the stabilizer group, then when you measure, you're always going to receive the measurement outcome -1. Right? So what happens when the poly P is not in the stabilizer group? Well, in that case, the outcome can either be +1 or -1, and you don't know which is the case. Now, in like a faithful quantum execution, a faithful quantum measurement, you're going to get +1 and -1 with equal probability, 50% probability, and just random. But remember, we're dealing in sort of like a slightly adversarial model here, or maybe perhaps a very adversarial model. Like the classical device has to return a correct answer, but it only has to return a correct answer which is consistent with some quantum measurement. So even if you ask it to make the same poly measurement multiple times, and even if that poly doesn't appear in the stabilizer group, it can sort of act as though it is in the stabilizer group by returning the same outcome every single time. So you measure something that's not in the stabilizer group, it'll just always report +1. So how do we sort of circumvent the classical device from doing something sort of undesirable like this? Well, at least I think you can maybe see what our goal should be, right? We're going to make a lot of poly measurements on our state, and we're going to hope that at some point the classical device is sort of forced to return both a +1 and a -1 for a particular poly element, right? Because as we just saw, if it returns a +1 and a -1, then that poly element could not have been in our stabilizer group. So if we've deduced that some poly element is not in our stabilizer group, we've made progress. We've learned something about our state, and we can just hope to iterate and learn more and more about our state. But so how do we, the real trick is how do we actually force it to reveal such a thing? And the technique we're going to use comes from the magic square game, if you've seen that before. So I've written out a square grid here, a 3x3 grid of poly elements in sort of a suggestive way. So let's make some observations about these poly elements here. So first, if you look along any row or column, you can see that all of the poly elements commute. And so what that allows us to do is it allows us to sort of measure all of those poly operators simultaneously. It doesn't matter which one we measure first because they commute. So we can measure along any row or column simultaneously. And secondly, if we look across any row and you multiply the polys there, you see that they all actually multiply out to minus identity. And what that's going to mean for us when we measure is that the measurement outcomes that we receive from measuring those polys must also multiply out to -1. And similarly, if you look at the columns of this matrix, then all of the columns multiply out to positive the identity. So if we measure a particular column, then the measurement outcomes for each individual poly must multiply out to +1. Right? And now you may see sort of the inherent tension here, right? There's actually no consistent way of labeling this square with +1 and -1 such that you satisfy all of the row and column conditions that I just mentioned above. So let me give you a sort of example for that. So suppose that we have this 2-round task, and in the first round we've asked the classical simulator to measure in some particular bases which correspond to the measurement-based computation of the string that we want. So G1 up to Gn applied to the 0, 0 string. Now, in the second round, we ask it to make some measurements on that state. So let's say first we ask it to measure the first row of this grid here. So by supposition, this classical device is giving us correct answers. So it sort of must satisfy the observation we made in step 2 here, in that the poly measurement outcomes must multiply to -1. And then after we do this, we can rewind the classical device back to where it had the state again and say, okay, instead of actually measuring the first row of this matrix, I actually want you to measure the second row of this matrix. I lied. I wanted you to measure the second row. And you can sort of keep doing this for all the rows. And then you can rewind again and ask it for the next column. Except now, when it returns a column, it has to satisfy this other part about observation too, which is that the measurement results must multiply to +1. So say it does that and it returns those measurement outcomes, and then you rewind yet again and you ask it for this second column, you rewind yet again, you ask it for the third column. Well, because of this observation 3 here, we know that there's always some poly in here which received an outcome which was both +1 and -1. And because it received an outcome of both +1 and -1, from the observation we made before, this poly element could not have been in the stabilizer group, because if it were in the stabilizer group, it would have received the same measurement outcome every single time. So great, we've made progress here. Like, we've deduced that the poly element XY is not in the stabilizer group of whatever our underlying state is. But now you might think, wait a minute, like, we deduced that XY is not in the stabilizer of either of the state that we have, the underlying state that we have, G1 up to Gn applied to 0, 0. But also, on the other hand, like, XY doesn't appear in either stabilizer group. Like, it doesn't appear in the stabilizer group for 0, 0, and it doesn't appear from the stabilizer group for ++. So it's like, in some sense, have we learned anything at all? Like, you know, of course, I could have returned XYD without having, you know, solved the problem at all, because I know that it's not going to be in either group. And the solution here is sort of conceptually simple, though it requires a bit of a calculation to get precise. But the solution is sort of simple. It's just to randomize the input. And it's not particularly critical how this randomization works. But sort of the upshot is that once you've applied this randomization to the input, like, all the inputs sort of look equally likely to the classical device. And so what's going to happen is, instead of receiving an arbitrary non-stabilizer of the underlying state, we instead get a random non-stabilizer of our state, right? And so if you collect enough random non-stabilizers of your state, eventually you're going to learn what the state actually is. And so if you've learned what the state actually is, then you can work backwards to see what the product of the GIs must have been, and then you can solve your NC1 hard problem. And that's actually it. That's the entirety of the proof. So I've prepared sort of one final slide here about the reduction, just as sort of like a summary. So once again, so the idea of the reduction is we have some classical device which is solving this 2-round measurement problem sort of by supposition, and we're going to use it to solve the Clifford gate multiplication problem. So imagine we have this classical device, and in round 1, we give it bases which correspond to the measurement-based computation of G1 up to Gn. And then the circuit outputs some measurement outcomes, and it commits to those outcomes. That's very important. And then in round 2, we ask it to measure one of these rows or columns of the magic square game that we saw earlier, and it reports the outcomes to that. And then we rewind, and conditioned on getting the same answers in the first round, we rewind and ask it a different question in the second round. We ask it a different row or column of this magic square game. And if we ask it sufficiently many questions, we're going to be able to extract a random non-stabilizer of our state. And once we've done that, what we can do is simply repeat this entire procedure again. So we sort of randomize our inputs again. We go through this whole thing where we give it all of the poly bases that come from the magic square game, and then we extract another non-stabilizer, and so on and so forth, until you've extracted enough non-stabilizers of your state that you can actually just deduce what the state is. Like, whatever's left over must be the stabilizer group of the state, which means you've figured out what the state is. Okay, so that's the structure of sort of the entire reduction. So I'll end here with just a few open questions and problems that maybe you thought of based on this work. So I only told you about sort of the NC1 result, hardness result, right? So that was on the narrow grid, but on the square grid, we can actually show that you can solve a parity L hard problem, which we think is actually like sort of significantly harder problem. But sort of accordingly, like, you know, the proof details actually also become sort of significantly more complex as well. The structure of the proof remains the same, but the details are just more complicated. But okay, that aside, you know, how can, you know, what should we look for going forward? Like, can we expect to prove harder and harder? Like, can we take the same problem and show that like larger and larger classical complexity classes still can't solve this thing? Well, at least in our case, the answer is sort of like emphatically no. We know that this 2-round measurement problem that I was just talking about is in parity L for Clifford circuits. So, you know, anything that we could have done, we could have solved with a classical parity L device. So something really has to give here. So you have to come up with something very novel, and in the most likely scenario is you're going to have to, you know, introduce an aspect which is a non-Clifford into the quantum circuit. But of course, once you introduce a non-Clifford element into your quantum circuit, you lose sort of like a lot of the nice algebraic structure that you had in the first place by dealing with Clifford circuits. And so, you know, the problem becomes pretty difficult. Another question you could ask is, well, what if we wanted the classical circuit to err with some probability? Like, you know, a lot of times, you know, we think of the quantum circuit as erring, like maybe we can also think of the classical circuit as making some kind of error. And it turns out in this case, at least for the NC1 result, we can still say something here. So this NC1 reduction that I just showed you still holds when the classical circuit is allowed to err with probability less than 2/75. And so there's some sort of natural questions here, like, you know, is this the optimal number? Like, okay, probably not. Can you prove what the optimal number is? Maybe by solving some sort of like large LP or something like that. And then a question we really don't know anything about is like error correction for the parity L case. So how would you allow a classical simulator to err in the parity L case? And of course, you haven't seen that result, so you don't know where the problems rise, but we don't know how to do it. And then sort of finally, you could ask sort of the reverse of that question, which is, can you allow the quantum circuit itself to err? And so this goes back to the original Bravyi-Gosset-König problem that I first talked about. There's a follow-up result by Bravyi-Gosset-König and Michael, which showed that even like noisy QNC0 circuits can solve this relation problem that NC0 circuits cannot. So there's sort of a natural question here is like, can we port those techniques to this interactive setting? And actually, like, we're working with like a summer undergrad right now who's working on some of these things, and it seems like, yeah, things are gonna to go through just fine. At least, you know, for the NC1 result, you know, this parity L result still sort of up in the air. Okay, so I guess I'm pretty close to out of time, and yeah, thanks for having me.
I have a question.
Yeah.
If there's time. On your last slide, that the one before this is open questions. Yeah, so you're saying you're repeating these rounds.
Yeah.
But if you're doing this reduction in AC0, this all has to be in parallel. Is that right?
That's correct. Yeah, yeah. I sort of talked about it as it's repeating, but there's nothing here about future rounds that depend on the previous round. So you can do all this repetition.
Okay. All right. Thank you.
Yeah.
Do we have more questions? It looks like our host has some technical problems. So, Michael, are you there? Can you talk? If you have questions, please unmute yourself and ask Daniel. My question. So your protocols are 2 rounds. Do you know anything?
Yeah.
2 rounds, like constant round or log round? I guess you will be low round because you are comparing low depth circuits. So you don't want the number of rounds to be too big, right? But
yeah, I mean, like, one of the really nice things about this reduction is that, like, it's a 2-round protocol, but actually, like, there's nothing about the first round which is actually important. Like, the first round is only there so that the classical device is sort of forced to have this sort of like 2-part strategy to solving the problem. Like, it just has to commit to its answers that it said in the first round. And so, like, if you were actually like, if you actually wanted to say, like, do this in a lab, like, okay, I don't know why you'd want to do that, but let's say you actually, like, did this in the lab, then, like, the quantum device, like, almost wouldn't, you could just, like, ask it all of the questions, like, up front, because, like, the quantum device isn't going to really change it all. And, you know, so as you add more and more rounds to it, it sort of becomes, you know, it's a less sort of desirable problem.
okay.
I guess maybe I have a question.
Yes.
Sure.
So I guess when the first result came out a couple of years ago, it was a fairly constrained result, as you said. But over as things have developed, it's been sort of made stronger and stronger. Do you have a sense of how far you think you might be able to push a result like this? Where do you think it might end, or are you really, do you think, quite at the limit of what this can
that's a really good question. I sort of think we're close to the end. Well, okay. In some respect, I think we're close to the end, because like a lot of the techniques that we're using really are like depending on the fact that we're dealing with the Clifford group, and like we know that sort of the complexity of the Clifford group maxes out at parity L. Like this is like a fundamental result of like Aronson and Gassman. So it's like if we're going to use like the same sorts of problems, it's probably going to have to max out at parity L, just because that's the difficulty of computing things in the Clifford group. Now there's a few other results that you might hope to get that are sort of intermediate. So like suppose that you like really didn't like the fact that this protocol was interactive, and then you wanted to make it like sort of like a one round thing again, where you just have this relation task. Then I think there is actually something to give there. I think that problem is actually hard. So I myself have tried to solve this problem. So one of the problems which I think is feasible but probably difficult is to show that this exact same problem, the BGK problem, that exact same problem can't be solved by like AC03 circuit. So like if you give it like a mod 3 gate, like it won't, like it's a problem about parities deep down. So like the mod 3 gate shouldn't really help it. But that result seems pretty difficult to prove. But that I think that would be interesting if someone could prove something like that. And then of course after that, it's just like, well, yeah, I mean, introduce some sort of non-Clifford gate thing and try something similar here to get an even stronger result about a larger complexity class. But I think that you're going to run into the problem that the people who are working on sort of general quantum supremacy have run into, which is just like you're going to start needing conjectures that are less standard. I mean, I'm happy to be proven wrong there.
Right, and if you want to think now, okay, well, how do I put this into a context? Can I map this over to an experiment where I can actually show something even in the presence of noise and imperfections? Is that something where you think there's an interesting direction to explore?
Personally, I feel like I haven't really yet been convinced that there's much reason to implement these things experimentally, because at the end of the day, like all of the protocols that I'm talking about are very easily simulable in polynomial time, and so it's like it's not clear that there'd really be any advantage to trying to show that we know that whatever device Google has cooked up, it's at least not a low depth bounded fan-in classical circuit. Like, yeah, maybe that's sort of interesting, but I think it's a lot less compelling than a lot of the other things that they're doing. But certainly, I think that in terms of feasibility, this problem is a lot easier to do in a lab, even when you add errors. Like I think you could strengthen the error results a good bit, and then even if you add errors, like you could envision Google having this done within the next 3 months if they actually put their minds to it.
Right, interesting.
More questions? If not, it's about time to end, and let's thank Daniel for this wonderful talk today. Thanks.